Okay, it looks like we can start. Welcome back, everyone. So it's a new day. The announcements seem like quite a lot of stuff here. I guess I got bored and just kept writing. But the big announcement is, of course, that we will have our first exam for the scheduled for next Monday. But before we go through the announcements, to start us off, any questions from you that you may have? Okay, well, let's just go over some quick announcements like we did before. Because it's our first exam, I've kind of repeated myself a lot, but it doesn't hurt to just go over this again. As far as scheduling your exam goes, since this is an online class with an in-person requirement for the paper exam, your exam is going to be done in a testing center. And depending on your preferred testing center, after surveying the class, I sent everyone an individual message through Canvas with instructions about the exam, further information about the exam, and how to schedule your exam. You should try to get that done as soon as possible, say right after class if you haven't done so yet. If you've already scheduled your exam, good on you, and it'll go pretty much that way for every one of the exams. But any questions about exam scheduling specifically, or other questions as well? Okay. Other thing that I'll repeat, just for the sake of driving the point home, since again, this is our first exam we're getting through, we don't have enough time for reviews on exams 1, 2, and 3. We will spend time reviewing for the final exam, but because we don't have a review day for exam 1, the actual questions I ask on exam 1 are going to be highly similar to the homework assignment questions. So getting caught up with your homework is the number one thing you should be working towards to prepare for this exam. If you can comfortably solve those problems, then you're in great shape for the upcoming exam. Be sure to put together your page of notes of the size 8.5 inches by 11 inches front and back with any information that you think will support you on this exam. And as far as assignments go, assignments 2.6, 2.7 are assignments that are due today. And Caleb says, where do we find how to schedule? Where I did was I sent a direct message through the inbox right here in Canvas. So you should have a message waiting for you there. But what I can do, just as an extra way to connect with you, is let me put down a quick reminder. And I can also send you an email specifically through Google so you can see it there as well. So let me put down a reminder to get back to first thing on Monday morning. Let me clear this out. Okay, there's my reminder. I better save that. There we go. So you should be able to find this in the Canvas inbox. Oh, awesome. I'm glad you see that. Let me delete that reminder. So it'll contain instructions and a direct link to the scheduling system to book your exam. It'll tell you the days you are allowed to book the exam, which are it's going to be open between the so-called official day, which is Monday, but to be flexible with everyone's schedules, it's open to be scheduled between Monday the 29th all the way through Thursday, July 2nd. Other questions at the moment? Okay. And just another comment to repeat from day one of the class, which was already feels like a long time ago. As far as the homework assignments go, there's two of them that are due today. So if you got 2.6 in, but you're falling a little bit behind on 2.7, that's kind of not too unusual. That's a lot of homework due on just one day. That'll happen occasionally on a weekly basis throughout the semester. If that's the case and you get 2.7, say, done tomorrow, or say even on Friday, that's completely fine. The due dates on this course are really just for the pacing sake. I put in a grade after the due date, but even if you got, say, a grade of 0 on something way back here, section 2.2, 2.3, 2.5, and so on, as you prepare for exam 1, go back to your homework, get anything that's missing complete, and I will grade them at full credit. So I'm not going to dock any late penalty or anything like that. I would say if you're getting your homework done and you took a little time to get through some of these sections, maybe your schedule is busy, that's not unusual for a fast semester like this one, you'll still get full credit. And it'll be very rewarding to help prepare you for the exam. Then once you're fully caught up with the homework, you've made your page of notes, I'd say that's a good time to turn around to start looking at the sample exam one problems. There's a lot of questions here, so it's not meant to be a document where you solve every single question, unless you had the time to do so. It's really what you would do is skip across section to section, do a few problems. There are various difficulties to get a feel for what all could be asked on the exam. But again, what's going to be asked on the exam are problems highly similar to what you did on the homework, which will be similar to what we also did as a class in the lecture notes. But that's my pretty much big spiel for the preparing for exam one. What we'll be doing next is going back to chapter 3 in 3.1. We cracked open the new chapter. It's all about the derivatives. Here we have the definition of the derivative, which will come up on exam number 1. The very last question will ask you to compute a derivative just like this one, using the definition, much like we did in sections 2.7 and 2.8. But now what we're doing moving forward in the schedule in section 3.1, this is content to now in exam 2, we're looking at what are the formulas for computing derivatives of certain specific functions, like say polynomial functions, short for poly, and exp exponential functions. So that's where we're at the moment. Any questions whatsoever, folks, before we jump back into 3.1? Okay, well, let's get started. We didn't get too far. I think we just spent basically the last 10 minutes of class on, what was that, Tuesday, yesterday, looking into some of the formulas for differentiation. So as far as chapter 3 goes, this is the major concept. We're going to look into formulas for differentiating certain kinds of functions, rather than having to resort to the definition of the derivative, which is right here, with the limit as h goes to 0 of that difference quotient. So the first big rule that we use all of the time, constantly, is the constant rule. If c is a constant like 0, 5, sine pi over 3 minus 1 was our another example, then the derivative of any one of these functions is automatically 0. Constants can be tricky. I think we mentioned that on day 2 of the class when we saw a constant rule for limits. Natural log 3 is also just a constant. Its derivative is 0 as well. And as a formula in Leibniz notation, that's what it looks like. d by dx of a constant c is just 0. The best way to spot a constant is inside those parentheses, there is no x variable whatsoever. So the derivative there is just automatically a 0. Well, the next rule of major importance is the power rule. If we have a power function, like say y equals x to the power 30, the process of differentiating those is kind of nice in a way. We mentioned that it would be torture to do it this way. If you have the time and the amount of paper to get through it, you can see what that looks like by just getting started. It's a painful process if you're just using nothing but first principles. But the power rule general version says we can do this in a very effective way. 30 just comes down as a coefficient, so you see it here. That's step 1 in the power rule. That's what the n is doing over here. Whatever the exponent n is, it comes down and multiplies as a coefficient. Then step 2 in the process, whatever the prior power was, it goes down by 1. So we went from power 30 to power 29, and that's what's being indicated here from power n to power n minus 1. So those were the 2 big review problems that we looked at. Or not exactly review problems. These were sort of the 2 big illustrative examples we looked at for these 2 rules. Any questions at the moment before we look into a couple more rules? Okay, the next big rule is the so-called constant multiple rule. It's nice to know how to differentiate a constant, nice to know how to differentiate a power function like x power 30, but you'll notice that this is still a pretty limited set of tools. If we want to say go from a power function like that to something a little bit more normal, like say 7 times x power -3. Well, this is a constant 7, a constant multiple of the power function, x to the power -3. And know the tools above, the constant rule, constant multiple rule, tells us how to differentiate that. But this rule here will allow us to differentiate that function. The constant multiple rule says if c is a constant, there it is inside the rule, but it's multiplying a bona fide function of x. We call it f of x here generically, but that's what the x power -3 is playing the role as. That's our function of x. Then the derivative of a constant times a function is just the constant times the derivative of the function. And you might feel like you have deja vu when you take a look into that. Let's take a look at the limit laws from section 2.3. From section 2.3, one limit law also said, if you have, say, a constant times a function, and you're taking the limit of that, the limit of a constant times a function is a constant times the limit of the function. Same exact idea, same exact process for derivatives. That's kind of a nice carryover. The reason this works in the same way is, well, the derivative is a limit itself, so you just use the limit law to prove this differentiation formula right here. So that's the formula. We're going to try it out with this function right here, 7 times x power -3. Any questions first before we illustrate it with a fast example? Okay, here's the process of what a derivative like the one down here is going to look like. Differentiate that. And y prime is going to become, well, the constant multiple rule says 7 as a constant is not affected. It just gets put down in a spot. And then you multiply it by the result of differentiating the function of x. So we're just going to take 7 times, differentiate this function. How do we differentiate it? We use the power rule on just that part right there. So 7 completely unaffected because it's multiplying the function this time. If it was 7 alone, it would have come out as a derivative 0. So that's the magic of the constant multiple rule. Now differentiate the function here. The power rule circled above says, whatever your exponent is, it comes down as a coefficient. So there it is, -3. Now multiply base x, and the new exponent, no matter what, no matter how weird that exponent looks, it always goes down by 1. So if it's -3, drop it again. Now it's -4. And that's the whole process. Constant multiple rule is kind of nice. It says, if they're multiplying, nothing happens to the 7. It just stays right where it is. And you multiply by the new derivative right here. So simplifying this, it's altogether -21 x to the power -4. So that's our next big tool. We still need more properties that's going to allow us to differentiate something like, say, a polynomial or a linear equation. We still can't even differentiate something like this, for example. Well, we can using the definition of the derivative. If we wanted to do it more effectively, and we had something like, say, 8x minus 9, none of the rules above tells us how to differentiate this, because these are two functions being subtracted now. But that's what the sum rule is all about. Well, it could be called the sum and difference rule. There's really two formulas here at once. But any questions or comments at the moment before we take a look into the new rule? Okay, just trying to get everything on screen, starting with the first one, the constant rule. So now when we look into this, there are a lot of formulas we're going to use. First, this formula says, if you have f of x plus g of x, or if you have f of x minus g of x, it's really two formulas in one through the plus or minus. So there's a version if it's just plus, there's a version if it's just minus. Then the derivative of a sum or difference of functions is the sum or difference of the derivatives of those same functions. So if we have a function f of x here, our f of x function is 8x, and another function g of x, our g of x function happens to be a constant one. It's always 9, and we decide to subtract these two different functions, then all we have to do is differentiate the first function minus the derivative of the second function. So that's what we're going to do to take this one on. Well, we're just about there, but any questions about the setup on this one? Okay, on the left, we have the function. You might have noticed I'm putting a comma because we don't want to say it's equal at this stage. We're changing to the new function. The derivative, either call it y prime, or if you're a Leibniz type fan, call it dy dx. We'll use that just for the sake of mixing it up and training our eyes to get used to that notation as being the derivative. So if we're going this route, the derivative of y with respect to x, we'll use the sum rule first, which says we can differentiate each of the terms independently of each other. Then when we go to differentiate 8x, we have to first use the constant multiple rule and then the power rule. So the derivative of 8x is going to look like this. If you want, you can put a power 1 on that x, and it's going to come out as 8 times. Power rule says 1 is going to come down and multiply that 8. The new power on x, well, that would be a power 0, but x to the power of 0 is 1. So we oftentimes don't even write that down. We just put in 8 altogether if we have a variable x. X just goes away at that point once we differentiate that. But for thinking of using the power rule, that's pretty much the process. Power 1 came down, multiplied, new power is 1 less, x power 0, which will simplify to a 1. Then we go minus, that's the sum rule with a negative sign in the middle. We differentiate the function 9. But 9 is a constant, and it's not multiplying anything that varies with x. So by the constant rule up here, the derivative of a 9 placed here is just 0. So we get minus 0. Oh, sorry, missed a chat. Caleb asks, d dx just means derivative. Yeah, absolutely. So when we say d dx, say on this version up here, d dx of a constant, this is how our author writes the formulas. In prime notation, we just could call that c prime if we prefer. Oftentimes our author writes it this way, so I duplicate it as it is in the textbook for the reading. But if you wrote it this way, just to say prime, so the derivative of c, you'd be saying the same thing. Does that make sense about the d dx? Or any other questions at the moment? Yeah, absolutely. 8 is the constant here. So if we drop that constant, say at 8 in that spot, the derivative would come out as a 0. So we put down, oh, sorry, I was thinking the 9, and even though I was saying 8. 8 is the constant right here. And so when we differentiate it, we're using this rule right here. 8 doesn't disappear, it gets copied in. Then we take the derivative of x power 1. So when we differentiate that, that's where the 1 came down, and we got an x power 0. So we used this formula on the x power 1 part, and then it gave us the 1 times x power 0, and then we use the constant multiple rule at the same time with that 8, which just says, much like the 7 here or the constant here and here, h just copies in. Does that make sense on the process of that 8 going in that spot? Not quite. If it was x squared, let's do another example over here. I think that one fits in more up on the power rule version. If we had a new example, say y equals x squared, and we were to differentiate that, we would say y prime is, let's follow this carefully. Let me get rid of this kind of a distracting set of arrows on there. So the power rule says whatever your power n is, it comes down as a coefficient, multiplying. So that power 2 comes down and it multiplies base x. Then the next thing that happens is whatever the exponent is, drops down by 1. So if it's a power 2 here, it's now a power 1. But often the way we would really write that, we would simplify it down because power 1 is just x itself. We would call that 2x, which conveys a power 1 altogether. Does that make sense for the x squared version? Yeah, absolutely. So anything that's a base raised to a power, this is the process. And this one was admittedly pretty weird because we wrote in the power, right? We started at a 1 just so that we could see what does it look like as a process. And that's what dropped it down to a power 0. But yeah, that's absolutely right. Then down below on this one, all that happens is we just get 8 when it's simplified all the way down. That's a 1 here, x power 0 times a 1 times 8. Minus 0 is still just 8. Other questions or comments at the moment? Okay, and maybe one more thought about this one, 8x minus 9. It's kind of a special function when you think about it. It's linear. And more than just that, it's not just linear, it's in y equals mx plus b format at the same exact time, right? Slope-intercept form. But remember, whenever you say slope in a calculus class, you should think, oh, derivative, really? So if you plot y equals 8x plus 9, here's the line right here. It goes through at, hang on, that's supposed to be minus 9. Let me try again. There we go. It goes through at negative 9. That's the y-intercept. And if we go up 9 and right 1, that's conveying that the slope, hang on here, up 9 and right 1 would be about that spot right there. So not quite there on the axis. So that would be the slope of positive 8 on this thing right here. So if your equation is linear, the derivative is just the slope m. So we can tell right away, either by analyzing, thinking about this being a line, thinking about the slope being just 8 itself, that the derivative is just naturally 8. It's kind of satisfying to see how every one of these rules, the constant rule, power rule, constant multiple rule, and the sum rule, all of them at once are used to differentiate this from scratch to get back to the 8. But it really was a foregone conclusion that if the slope is 8 on a linear equation, that's the m, then the result here has to be 8. It has to flow in that way. Only works for a linear equation, sadly. Well, we'll try out another one. So far, we have a good set of rules, and this is most of our way through. Combining all these together is going to allow us to calculate the derivative of a lot of different kinds of functions. And maybe just for the sake of another example, let's put those two examples down below. Let's do another kind of warm-up type problem before we get to the next ones. If it bumps up from, say, linear to quadratic, let's call it 3x squared minus 8x plus 14, we can use all the rules once again to differentiate this one really, really fast. And here's how the process goes. Y prime, first there's 3 terms, but that's okay. The sum rule is stated for 2 terms, but it generalizes into any finite number of terms whatsoever. Whether there's 3 or 300, the rule can be used. We're just going to differentiate term by term by term and maintain the signs we have in the middle. So let's start here. That's a 3, a constant multiplying a function, x squared. Constant multiple rule just says 3 copies in, and we multiply by the derivative of x squared. And we did that up here, but let's still think about it from scratch. When we differentiate x squared, 2 comes down as a coefficient, and the new power of x is now a 1. But when this drops to power 1, it's traditional to just leave it as x. It's most simplified form now. So that term is done. And then we just move off to the next term, the derivative of negative 8x. Big idea here is if it's x power 1, sure, you can say it's 1 times x power 0, and then it just gives you the constant in front, but that was only for the sake of a demonstration. That's a foregone conclusion that will happen every time. So if it's just x vanishes when we differentiate, and you keep the constant, negative 8. So negative 8 copies in, much like when we differentiated this 8x, we just got the 8 altogether. And then finally, the last term is 14, but that's purely constant. The derivative of a constant always goes to 0. We don't always put in the 0 there because it's a foregone conclusion. So if you put plus 0, no harm done. Well, often once we differentiate more and more of these, this is pretty much all we would write. We know that that vanished, it being a constant, so we would just leave it in that form and simplify it to a 6x minus 8. And then our work is 100% done at that stage. So that's what differentiation looks like at the moment. We just go from term by term, using all the rules that we have above to support each portion that we differentiate. Well, we're going to look into exponential functions next, and then look at a set of just practice drilled style problems to get better and better practice at this. Any questions or comments at the moment with that latest example? Caleb says, could we see it in graph form? Yeah, absolutely. As a graph, we put in the y equals 3x squared minus 8x plus 14. We get this nice looking quadratic function up here. And now we can kind of guess, what is the derivative going to look like? Well, on this end, it's going down. So all the tangent lines are going to be negative until it hits a horizontal tangent line. Let's suppose we are freehand sketching this just to get a feel for it, an extra practice. There's a horizontal tangent line there, so that means the derivative should intercept the axis right there. Then on this range, the derivative is always going to be negative because slopes of tangent lines always go like that, negative slope. So if the function is decreasing, the derivative is negative. And so if I make my derivative be negative, again, this is freehand, so this might not be fully accurate. That would do the job. It's always negative until it hits the horizontal tangent line. And we draw it a little bit better, kind of like that. Then when we're on the right-hand side, it's going up. Tangent lines are always positive, and so the derivative should also always be positive. So here's what it would look like if I were to freehand draw it. And notice what I did was, the original equation is quadratic, but when we differentiate a polynomial, degree goes down by 1. That's why I try to draw something that's linear. The highest power here is going to be power 1. And it's also why we got something that is linear. Now that's the bona fide equation. I'm pretty sure my y-intercept is way, way off on this, but let's put it down and see how close or how far I got. Y equals 6x minus 8. I got one part definitely right. I got the intercept, but I didn't make my slope as steep as it needed to be. The slope had to be slope 6. Mine looks like it's probably slope 2 or something. But if we clear the annotation, and now just focus on both of these curves, here's the original function. The slope is negative, so the derivative is negative. But the change is less drastic as you get closer to that turning point. It suddenly becomes flat. Horizontal tangent line will give us that point there. And then it just goes upward. As far as the y-intercepts go, they don't necessarily relate to the derivative. It's always going to be about the slope of the tangent line specifically, not necessarily a y-intercept here at roughly 14 doesn't necessarily give us the information about the derivative. And one way to think about it is the y-intercept was that 14. And notice I could make it be an 8. But the green line never changed. I can make it be a 0. Green line's still fixed. Make it be a -3. The green line never moves no matter what you put here. And for emphasis, let's just put in a slider. No matter where you put that y-intercept on this graph, the derivative is always the same. That's because the derivative of that 14 just goes to a 0 being a constant, and you're always getting just that function there. Caleb says, so we can always ignore anything without an x. Yeah, absolutely. What you said there is basically what this is, the constant rule. If there's no x, you're differentiating a constant, it's going to be a 0. And so ignoring it just means that 14, it's gone in the derivative, and that's why we ended at -8. Other questions or thoughts so far? Okay, thanks for all these questions. These, again, for the first time seeing differentiation rules like these, those are the kind of questions you would want to ask to see how they all relate together. And great suggestion, seeing it through the graph. Sometimes that's a great way just to see how the ideas combine. This is thinking about it geometrically, whereas down here, everything we're doing is purely analytically. It's just formulas and numbers that are being pushed around. So it's good to relate the two. So far, we've been looking into, let's look at the title, polynomial, but there's also EXP stands for exponential functions. And this is going to be the next set of derivatives. There's going to be the derivative of the natural exponential function and the general exponential function, a to the x. When we say natural exponential function, it's no different than saying natural logarithm. What it means is the base is e. Euler's number, it came up earlier in the notes. I think when we're looking into limits at infinity, about 2.71 and some change. If you put e into a calculator, you get this out. 2.718, 218, 282, 46. And depending on your calculator, you might think that the decimal maybe repeats in a certain chunk, but it's not true. It's irrational, just like, say, pi or square root of 13. So these derivatives are really kind of bizarre. The derivative of e to the x is itself. Let's think about that for the moment. If the derivative is itself, then when we go to plot y equals e to the x, what we're effectively saying is, zoom in just a little bit, anywhere you go here that you put a tangent line down, the slope of the tangent line is exactly the function value. So right where it intercepts on the y-axis, the function value is a 1, but that's also the slope of the tangent line. The tangent line there is exactly y equals x, which has slope exactly 1. If you go to a different spot, say, put in an input of, try to get to 1 here. Really tricky some days. There's 1. If you put in 1, you get 2.71828 e again. What it's saying is right at 1, the slope of the tangent line is 2.7128 altogether. So this is the world's most bizarre function in a certain sense. It's the only function that has this property. Its derivative is itself. The function itself describes the slope to its tangent line at any point x that you throw inside of there. Really kind of a bizarre function. And it's not too much you can do for a fast example on this one, other than maybe write down a y equals 5e to the x. If you write y equals 5e to the x and differentiate this, you get y prime equals Well, there's a constant multiplying e to the x, so you would put down 5 multiplied by the derivative of e to the x, but that's itself. It's just 5 e to the x. So nothing happens when you differentiate that function there. Well, let me get rid of that annotation. So this function, multiples of it, have these weird kind of features going on. But notice how dangerous this is as a process. If you're differentiating 3x squared, or if you're differentiating ax and so on, the process for x squared is 2 comes down, multiplies, and the power goes down by 1. But that's because this was a power function, x squared, and we use the power rule for that. But if it's exponential, that means x is no longer a base like we had over here at x squared. If x is an exponent, this is the process. X does not come down at all. That only works strictly if x is the base and the exponent is constant, n maybe 30, like in this example over here. So this is where it becomes tricky in a certain sense. We have to separate in our mind which functions look like these, power functions or polynomials, and which functions look like these, the exponential ones. Exponentials always have x in the exponent position. Then, if you differentiate something like this, a to the power of x, these are the ones that are just a little bit not as nice, but still kind of nice in a certain sense. We really like the derivative of the natural exponential function, and we really like natural logarithms. One reason is the derivative is nice. It's just e to the x. If you go to a different base, say a, your function is maybe y equals 13 to the power of x. Differentiating this is not just 13 to the power of x anymore. You have to multiply it by the natural log of the base, whatever that base happened to be. So if we differentiate that function y there, we would say y prime is still 13 to the power of x. That part doesn't change. But then we multiply it by the natural log of the base, which is 13 itself. So this is the generic formula. And the only reason we don't use it up here is because even if you did use it, natural log of e is exactly 1. So it's as if you're always using that formula, but if your base happens to be e, because natural log of e is 1 exactly by properties of logarithms, it simplifies in that one and only one case. So they're both important to memorize. This is the generic version for an exponential function, which will come up plenty. And this is the nice simplified version, which does seem to come up more often than the version down below. So that's our list of new differentiation formulas in section 3.1. What we'll be doing after this is just practicing with these brand new formulas. But any questions or comments at the moment with any one of these? Okay, so this is what calculus looks like so far. Calculus course is kind of weird because it has to start at the foundation of limits. Limits are the major foundation of calculus. They define continuity, differentiability, what we're doing here, and later integrability. But when we go to actually really focus on derivatives in chapter 3, notice it's just a weird little number game where sometimes 2 comes down and multiplies. Other times when you differentiate, nothing happens. And other times when you differentiate and you notice it's exponential, you just tack on a natural log of 13. So we just have a new kind of algebra of how to rearrange things and get the derivative as fast as possible. Putting everything together, here is the next slew of problems down below. And this is the one revision. I forgot to write it equals and a function here. I just had this part all alone. So these are the typical kind of drill exercises, same kind of problems you'll see in the homework set, where now we have more built-up functions, and all we're doing is differentiating them. Or said differently, compute the derivative or evaluate the derivative or Sometimes instructions in the book just say differentiate, and that's all you're doing. I would encourage you, because it does become useful and relevant in chapter 4 in particular, to label your answer. If the function is f of x, it becomes a really good idea, and you'll see why in chapter 4, to label it as f prime at x. In chapter 4, sometimes we have to use the function f, then we have to use the function f prime, then we have to use the function f double prime in different steps for long convoluted processes in optimization. And not labeling what is what makes it really, really hard to untangle what goes where. So our answer is going to be f prime at x. And here's the process. We'll say the rules as we go and why we're using the rules. First rule is the constant multiple rule. -2 is multiplying a function. So it copies in and multiplies the derivative of that function there. And just for a refresher, when we differentiate x cubed, we're using this formula. Derivative with respect to x of x power n is n times x power n minus 1. So there's our power rule refresher. But that's just a game with the exponent. Exponent comes down, converted to a coefficient, multiplying x to a power 1 less. It's now power 2. If it was power n, it comes down as a coefficient, multiplies base x to power 1 less, n minus 1. So this is the general formula version. And here's the portion for that particular example, x cubed. So once we do 1, we just move down the list. The sum rule says we can go plus and just differentiate the next term as we go. Any questions at the moment with the first term down? Okay, now next term, same song and dance. Sometimes when you get really well practiced at this, you might just write down the overall answer, but we're studying this in bit by bit. We're looking at each component. So if you start off by going 4 times, that's the constant multiple rule, and then you went 2 times x, that's the power rule, that's not a bad step to take at the moment. But if you put down, because you're visualizing 2 coming down and multiplying, so you put in an 8x, that would be a great shortcut to take. We'll start doing that a little bit more and more, the more we get practice doing these kind of derivatives. Again, the power went from 2 to a 1, so we just leave it in that as its simplified form. That implies power 1. So that's 2 derivatives down, separated by plus, so we use the sum rule again. Then when we go to differentiate e to the x, that's kind of like a celebration in a way. That's the world's nicest derivative. Derivative of e to the x is just itself. We just had to be prepared for that we had to know x doesn't come down. The new power is not x minus 1 any longer. This is the new result. And then last, our final derivative for -9, there's no x there. So we are done. We can ignore it because the derivative of -9 is 0, and going -0 or +0 makes no difference in the derivative. We still have to simplify our answer, but our work is done. We can just say f prime at x is -6x squared plus 8x plus e to the x, and nothing further to do. So this is a stage at which derivatives become kind of nice, because all of the derivatives we took in section 2.7 and section 2.8, they were all kind of a long slugfest of write down the limit as h goes to 0 of f at a plus h minus f at a divided by h in section 2.7, and those limits sometimes get really busy. But here, with properties of the derivative, this is all we have to do. The answer is just that. So that's one down. We'll practice several more to get a good feel for these. Any questions or comments with this one? Okay, here's where it gets a little bit weird. If you have something that looks like this, the derivative of this function is not the derivative of the numerator divided by the derivative of the denominator, unfortunately. And there's a lot of derivatives that, we just can't take quite yet. There's a whole rule for handling something like this in the very next section. But for a problem like this one, the best thing we can do is simplify it down. This is just not a good algebraic form for doing the derivative like part A was. What we want is a bunch of terms that look like that. X to a power of something, n, maybe with some coefficient. But if we use properties of exponents, we can make that happen. First observation we'll make is that the square root of x is nothing but x to power 1/2. Finally, we have a nice exponent rule that says x power n divided by x power m is x to the power n minus m. And when we use both of these rules together, we can force all three terms in the numerator to look something like that, x to the power n. N can be any real number whatsoever. It can even be a fraction, like it's going to occur in this problem. And so that's the strategy on part B. So some of them go pretty fast, like part A, because there was no preliminary algebra we had to do. But on this one, here's our first step. We need to fix it algebraically to get the answer we need. So we go 3x squared. But instead of x squared, we can rewrite that as power 4/2. It can be divided by the square root of x, but we're going to write that as x power 1/2. Then divide root x into the next term, go minus 6x. That one has power 1, but you can write in a power 2/2. Divide by square root of x, which is equivalently, as a rational exponent, x power 1/2. Then go plus 7 over x power 1/2. So far I made the problem look worse, but that's because our only major tool is that one right there. We don't have any formula yet for derivative of a quotient division of functions. That's in just the very next section. So here's our first step, rearrange it algebraically. We're still dealing with just y, so I'm labeling it as y. And now we use this quotient rule over here to the right for exponents. Here, we can copy this in as 3. The base x, where it's power 4/2, minus 1/2. That will give us power 3/2 altogether. So all we have to do is just subtract the exponents in that way. Works again on this one, we get minus 6. X, the power is 2/2. 2/2 minus 1/2 will give us positive 1/2 altogether. And then we're on our way. We need one more rule for this one, though. If you have something like this, 1 over x power n, that's not convenient to us either. We don't want to differentiate this one. It's not the derivative of the numerator divided by the derivative of the denominator. I mean, if that was true, the derivative of the numerator would be 0 divided by the derivative of the denominator. And this whole thing would be 0, but that's false. The derivative of this is not 0 whatsoever. So whenever you're dividing or multiplying functions, differentiation formulas get more convoluted. Our best bet with this one, to again make it look like that. The idea is we want base x to be up in the numerator, never ever in a denominator. So the exponent law says if it happens to be in a denominator, you can just rewrite it. You change the sign by negating it. So if it's positive here, it'll become negative here. If it was negative down here, it would have become positive up here. So on this one, we just go plus 7. If it's x power 1/2 down below, you can write in x power negative 1/2. So that's one way to correct this exponent. And now what we have is something very similar to what we had on part A. We have one function here, another function here, another function here. We don't have the constant, but we're just going to differentiate going term by term by term, just like we did in part A. It just needed some algebraic surgery, some exponent work to make it happen, because this is our major idea for differentiating these kind of functions. Well, any questions at all, folks, with the algebraic side, getting it into the right format to use the power rule here? Okay, now that it's in that format, derivative goes pretty fast. We have, I'll call this just a generic y prime this time, just like we did over here with these functions. If we differentiate here, that's the constant multiple rule. 3 multiplies, then we take a breather, analyze the function. It's a power function, just a weird power, right? 3/2. That's okay, 3/2 plays the role of n. It'll become a coefficient, so 3/2 goes over here. We multiply it by base x, and then we subtract 1. So subtracting 1 from this is just 3/2 minus 2/2, and that would give us a 1/2 altogether. So that's the first term down. Then rinse and repeat. Same song and dance on this one. It's -6 multiplying through the constant multiple rule. The new exponent is 1/2. So that's the n up here. It multiplies in front. So here's the 1/2 multiplying. Then our new power x is 1 less. But if we're taking 1 less from 1/2, that's just subtracting 2/2. Let's say this here just for an emphasis. This was 3/2 minus 2/2. And this is going to be 1/2 minus 2/2. That just gives us a -1/2 altogether. And then we just do it all over again. Well, +7 multiplied by, constant multiple rule says multiply it by -1/2. We update the power of x where the red dot is. We subtract 2/2 because that has the least common denominator with -1/2. That would give us -3/2. -1/2 minus 2/2 is -3/2 altogether. So here's our function. All we need to do is simplify. Y prime is 9/2. And it's up to you what you want to do with this. I'm completely happy as x power 1/2. You could call it square root of x if you like. I'll leave it in this format, x power 1/2 to convey, that's completely fine. On this one, it becomes -3. And it's up to you what you want to do with on this one. I don't care about negative exponents, so you can leave them just where they are. Or you can throw it into the denominator with x power 1/2. Or you can throw it into the denominator with the square root of x. All of these are completely equivalent algebraic forms, as long as it's simplified by taking care of the reductions here. If you leave it even with a negative exponent of -1/2, completely fine with that. Here you're focusing more on the calculus, not getting bogged down on the algebra, rearranging it more and more. But that's always an okay stopping point. Last, this is -7/2. And same comment, I would probably just leave this one in my own personal work. You're welcome to do so as well in your work as -3/2. And if you decide to go further on that, any equivalent algebraic form of base x to a power -3/2 is for full credit as well. So that's our answer, our second derivative in example 1. Any questions or comments at all, folks, getting through this one? Okay, well, it was a complicated function. The derivative is equally complicated in a certain sense. Now for the next one, I think it's a bit of a breather compared to what we just did. We have -5 times x plus 1 squared. But you know that's some reason for concern, because when you look at this carefully, this is really a -5. Constant multiplying a function is not the problem. The problem is x plus 1 squared is a product of functions. That's really x plus 1 times x plus 1. And the reason that's so concerning in calculus is the derivative of x plus 1 times x plus 1 is not the derivative of x here, which is a 1, times the derivative of x here, which would be another 1. That would make the whole answer -5, but that's not true at all. The slope varies at every single one of these points. The slope is not always -5. The next section will tell us how to differentiate when functions multiply. But even if this function came up in the next section, we'd probably still just expand it. Much like over here, if things are being divided, we should just actually divide and simplify. Same idea, if things are being multiplied, we should just multiply it out, simplify, and then take the derivative. The next section again tells us another process for differentiating a product, but we don't have to get that convoluted at all in this particular section. So next step I would take on this one is to write it as -5, FOIL out x plus 1 times x plus 1. You get x squared plus 2x plus 1. Distribute the -5 through, and you get -5x squared minus 10x minus 5. Again, kind of a nice breather after getting through this more convoluted one with all the exponent work. Here's the function g of x in its most simplified form, simplified for the purpose of differentiating that function. If we want to differentiate that, g prime of x is going to be same process as we did before up here on this line, but slightly nicer exponents, so it looks like it's not as abstract. But really, it's the same kind of idea. -5 is going to be multiplied by this exponent 2. New power on x is 1, so we write in just x itself. Here we copy in -10, but whenever x occurs, x alone like that to power 1, well, it's a linear function with slope -10. That's the derivative. Or the power rule itself would say the power is 1 would come down and multiply it. Still, it's -10. New power on x is 0, but x power 0 simplifies to a 1. So we just leave it in that form irregardless. The next -5 term is a constant, so when we differentiate that, it goes to 0 and our work is now done. G prime at x is -10x minus 10, and there's nothing further to that story. Again, there's a lot of caution to take on these, right? If you said that this should be -5 times the derivative of x is a 1, and maybe go 1 plus 1 for a 2 and even square it for a 4 and get, say, maybe -20, still it's not right. The derivative is to power 1. It's a linear function because the original function over here is a degree 2 quadratic. The degree only drops by 1 when we differentiate. So watch out for these kind of things that happen in the homework. If you notice that there's more going on, a division or a multiplication or even a group squared like that, you need to take the algebra further, simplify it down into forms that look either like this. That's a great form for differentiating, or like this. That's a great form for differentiating, and then start using the properties of derivatives. So those are the two cautionary tales on parts both B and C. Any questions or comments whatsoever with either derivative? Okay, well, let's try out the next one then. This one seems to have a lot going on, but not really. It's not really too bad. The 2x term is just fine. That's ready to differentiate. The 9 power of x term is ready to go as well. It's all about what's happening in the middle. So for this one, let's hide example 2 for the moment. Good way to start is let's just do some exponent work, focusing on what's going on right in the middle here. First, let's put down a property of exponents whenever we see anything of this form, a radical expression mixed with exponential, x power 2. The formula goes like this. If you take the nth root of x to the nth power, then this becomes x to the power of m divided by n. There's two exponents you have to put together, but really only one degree of freedom in a certain sense. If you remember where the root goes, always in the denominator, then you'll always know where the power m goes. The inner power is just going to be what's left over. So think of the root as always just going over here. In fact, we wrote that once already, right? we said square root of a could also be written this way. We just don't always indicate the index. If you put an index 2, you could leave it like that, and it's implied it's a square root of the index 2. And that's a power 1/2. Same idea. The index, the root you're taking, goes in the denominator. So that's the first idea we can put together. Now, if we take that entire chunk, 5x times the 5th root of x squared, we can rewrite this as 5x times x squared divided by 5. I said that weird. X to the power of 2/5 is the better way to say that. So I took the 5th root, index is 5, divide it into power 2 for x. This is what we get. It informs us on how we should write the exponent on x. It's truly an exponent 1, but now we can say it's exponent to of 5 divided by 5, still a 1, times x to the power 2/5, which means this is all together 5x times x to the power 7/5. Now we're ready to go. The reason we take all of those steps to get down to this point is the one major tool that we have is that power rule. I think I have it right here if I can pull it up quickly. Let me try again. Hopefully it doesn't open like 3 copies of Microsoft Word. I won't open that up because I already have it open. My bad. Let me just copy this down. That's a little bit faster way to put a file down or an image. Okay, so that's the idea I was trying to connect together. The reason we took all those steps algebraically is because the major tool that we're using is this power rule right here, which insists we need to have the base x in one spot written to 1 power, and the base x also has to be in the numerator. So things are smeared around like this. That's a product of 2 different functions. We have to put them into one function overall to use that formula. But now that it's in that form, our work is ready to begin. We can rewrite y as 2x minus 5 times x to the power 7/5 plus 9x. Now we're ready to get going, but let me also copy down another rule that we haven't used much in these notes. The rule said d by dx of a to the power of x. That's now an exponential function, so it's a to the power of x times the natural log of a. We need that for the 9 power of x we see here. So now we're ready for the derivative, dy dx, or just y prime if you prefer. Going left to right, term by term. The derivative of a 2x, just a 2. Whenever x is to power 1, it vanishes, and you just keep the coefficient. For this part, we copy in the coefficient, -5, through the constant multiple rule. Now use the power rule. The n right here is 7/5, so it says it should come down here. So here's 7/5. The base x multiplies. Now we subtract 1. But if we have 7/5, subtract 1 is just subtracting 5/5, giving us a 2/5. So from here to here, that was just 7/5 minus 5/5. So that's 2 terms down. Sometimes you might notice that the algebra takes more time to think about and work through than the actual calculus in this section, depending on the problem. Now last term, 9 power of x. All we're doing is we're taking that 9, that plays the role of base a here. This will be plus 9 to the power of x. That's this part where a is 9. There's a little bit more to the story. You multiply by the natural log of 9. Then at that stage, our work is almost done. We still have to simplify all of our problems, but that's just canceling the -5 divided by 5 in the 7/5. So dy dx reduces to 2 minus 7 times x to the power 2/5 plus 9 to the power of x times natural log of 9. And that's nothing further to say on that one. Looks like so far the harder problem that we did on the notes was possibly part B because of all the division work. But any questions with this one? Okay, and I noticed that on part C, I just want to put a little box here to convey that was my answer, because some of my notes got a little bit close to that. The kind of idea here is you want to always try to write your math so it flows and things don't seem like they are glued together like in a cloud of math symbols that might be hard to read your own work if you came back to it a week later. So if you need to, put a box around stuff to emphasize where an answer ended and a new thought began. You don't have to box out things if it flows nicely, but if it helps your eyes, no harm doing that. So that was our part D derivative for our run through of the differentiation formulas we saw in these notes. I have two more problems I want to take a look into, several more problems I want to take a look into. One is going to be a tangent line equation just for showing the process again. And another one will be the application problem down below, making some of these ideas more concrete. So first, let's take a look at the tangent line kind of problem. This is a tricky question because we focus pretty hard on what tangent line process should look like if we were in section 2.7. In that section, same with the homework and same with the exam number 1, we'll ask you to use the definition of the derivative. But when you're in chapter 3, it's implying that you're now using properties of derivatives. And so there's a whole new process to this one. To find the equation to the tangent line to this curve, it's complicated. There's a degree 4 power function term and an exponential, so a very complicated function. But yet, it still has a tangent line. It's differentiable everywhere. And we want the full equation of the tangent line at the point 0, 2. So let's plot this out just to see if we're getting on the right track. Here's y equals x power 4 plus 2e to the power x. And we're interested in the point 0, 2. This informs us that the tangent line should be going this way. It should have a positive slope, and we want the exact equation to that. So first thing we need to build that tangent line equation is its slope. That goes back to an earlier comment. When you think slope, what you really want is the derivative. So the entire step 1 to this process is just differentiate. Take dy dx, or y prime if you prefer. Term by term, this one's not too bad. This will become 4 times x power 3. So that's our good old power rule in action. I think I can scroll up to show it. That power rule right above. 4 came down, new exponent on x is just a 3. Now this one's really nice. We use the simplified version of this rule, which says d by dx of e to the x is itself. And it doesn't matter if it's being constant multiplied by 2. The constant multiple rule will say this is plus 2 times the derivative of e to the x, which is e to the x. So that's the entire derivative. And that's the end of step 1. Any questions at all, folks, getting through the first step? Okay, so now that we have the derivative, we have the slope to this equation at any x coordinate whatsoever. But the one that's relevant to us is x coordinate 0. So we go to that one and only coordinate. Here's the formula for every slope all at once, but we're going down to 1. So in step 2, the slope we want, I'll call m. Let's give it a special color. M is going to be equal to dy dx. We want to evaluate this at x equals 0. So this is the notation that we were looking at in section 2.8. dy dx is the derivative. That's the evaluation bar. It says evaluate at x equals 0, but all that really means is input 0 in for x in the formula that you see above. So this becomes 4 times 0 cubed plus 2 times e to the power 0. So here are those two substitutions. E to the power of 0 is just a 1, so this becomes 4 times 0 plus 2 times 1. That tells us the slope is 2 altogether. And based off the picture, right where that green dot is, that looks plausible. It has a slope 2. It's not terribly steep. Doesn't look like a slope 1 either. And it's positive, so that's the major thing. That looks like we're on the right track. So we've got a slope, came from our derivative. For step 3, we just put it all together and build out the tangent line equation. So here's how we did it on, I believe we might have done this on day 1. We take y minus y1 multiplied by slope m times x minus x1. Running out of colors, but we can color y1 as yellow, I'd say. That should work. So using all the information we have here through the color coding, this becomes y minus 2 equals 2 times x minus 0. So here's the 2. Here's the 0 given from the original point, 0, 2. There's our slope m is 2, substituted inside. And so now this is y minus 2 is 2x. And so the tangent line equation is y equals 2x plus 2. So the claim is that's the right tangent line equation. And for doing this as a homework problem, we can't do this in an exam setting, but it's a great idea to take advantage of this in a homework setting just to get further intuition. Plot your line, y equals 2x plus 2. And if it looks about like that, you have the right tangent line. The feature of a tangent line is it's the best local linear approximation to the complicated function x power 4 plus 2e to the x. Nearby, x is 0. So if we zoom in more and more on this, the blue line, the original curve, and the purple line, the tangent line, they should become indistinguishable. So if you do that kind of process on a graphing calculator or on Desmos a little bit faster, this is about what you should see. And look how sensitive this is. If you got this off, even by a little, say you put in 1.9, you can tell the difference there on 1.9. Zoom in more and more, and you can see this doesn't quite look right. They're off. They're not becoming the same. In fact, the more I zoom in, the more different they start to look. So even if you're off by a little, you'll probably know right away on this kind of process. Well, that's our redo of the whole tangent line equation process. In this chapter number 3, it's really always going to be a 3-step process in this kind of way. Any questions at all, folks, revisiting tangent lines? Okay, so the derivative gives us the slope of the tangent line at any point whatsoever. 2 is just the derivative of the function evaluated at one number, 0. And when we say tangent line, we have to have a point, and that's the picture it gave us. The best local linear approximation to the original function up above. So now this was a decent application in its own sense. We can now solve the problem that we did on Monday of last week really, really fast. So that's kind of satisfying in a way. We did that in a painstaking way on the very first day of class, trying to solve one of these kind of problems. And now another great application could be something along these lines. Functions, random functions like, say, these, can model all sorts of stuff. They can model amounts of mass in a nuclear reactive safe site. They could model, say, a population in a specific region. They can model the amount of, say, spread of a meme on the internet. For a random example, that'd be just fine. And functions can model lots of things going on in a biological setting as well. They can model the rate of a reaction, the concentration of a chemical at time t. But here we're going to turn to biology for a particular example, just because it's a little bit easier to visualize. Here's what it says first for this one. biologists have proposed a cubic polynomial, so that's why you see a power 3, to model the length L of an Alaskan rockfish at its age A. So we're thinking about fish. And if you see this as a homework problem, this is a decent strategy all on its own. As you're digesting the problem, type in Alaskan rockfish. And sometimes just having a mental, don't know why I have to say I'm not a robot or put in taxis. Hang on, let me try this again. Alaskan rockfish. Okay, I'm not going to solve a CAPTCHA. Looks like it really wants me to. Hang on, I think this is a good enough one to solve a CAPTCHA on. I think I see a bicycle here and here. I might have missed one. Call this a mental break. Okay, now we can look at the images. And the idea is if you see an applied problem like this one, sometimes they feel really abstract, but any information you can get when you're doing a homework problem at home to take a look at what you're dealing with, it actually helps. This is the Alaskan rockfish. Now we have a mental image. We're talking about the length of that fish at a particular age A, and this is the formula that models it. So L is the length. They're kind of interesting looking fish. Here's the length, that's the dependent variable, much like the L or the Y variable in the prior problems. The independent variable is A, measured in years, and goes in these particular spots. We want to calculate DLDA. But we also want to do an evaluation. We want to do it when A is 12. And once we do that entire thing, we want to give a practical interpretation using the context of the problem. So we're going to look at these kind of problems more and more as we go throughout the notes. Chapter 4 will be more about optimization, but same kind of ideas. It's kind of a tricky problem to do for the very first time, not because the calculus is tricky. What's tricky about it is it's one thing to compute this number. We did effectively the same thing when we did part 2 right here. But it's a whole nother skill to say concretely in context, what did we really compute? So let's go through this one carefully and in stages. Step 1, first, just do the derivative, DLDA. Then over here, we're using the same ideas as before. Think of A as being like a variable X. Constant multiple rule says this will just be 0.0155 multiplied by the derivative of A cubed. Power rule says 3 comes down. And the new power of A should just be 2. Not should be, is 2. Should make that more definite. So that's term 1 down, and we just rinse and repeat. Next term, because that's a constant multiplying, we copy it down, negative 3.7. Let me try again, negative 0.372. Then power rule here says this will be 2 times A to power 1, so just 2A. Do it again on this one. A is to power 1, so it vanishes, and we just get plus 0.395. Last term is a constant, so it goes to 0. And so we're just about done. We should simplify some of this stuff as we go, though, so let's simplify it. Here's our rockfish again, but let's go to a calculator. So we have 0.10155 times 3, 0.0456. A squared minus, might be able to do that in my head, but you know it's honestly too late at night to be too confident with that. When you're getting tired, arithmetic is one of the first things to go in math. So 0.744 times A plus 3.95. So there's the function simplified down. Oh, thanks for spotting that, Ashton. 0.0465. Looks like I transposed those two with a 6.5 there. Good eye. Thanks again for spotting that one. So with that full derivative down, Again, just like on the tangent line problem, although we're not doing a tangent line on this one, we just want the slope really. We move to the next step and evaluate when a is 12 itself. But any questions so far with the result of the derivative? Okay, let's do it again, or not do it again, but rather go to the next step. DLDA. We're talking about the derivative, but we want to evaluate that derivative when a is 12, which just means we're plugging 12 into the independent variable a in those two spots. So this is 0.0465 12 squared minus 0.744 times 12 plus 3.95. At this stage, it's just a big calculator operation. And this is a decent reminder for the sake of exams. I don't think we'll use a calculator a whole lot on exam one, but this is an example that can occur on the second exam, and you would need your calculator for these kind of problems. So best practice is don't forget to bring your calculator to the testing center just to get into that pattern on every one of the exams. So fast computation here is going to give us 0.0465 times 12 squared minus 0.744 times 12 plus 3.95, double checking the digits here, we get 1.718. We're pretty much done, but we should go a little bit further. And I saw people do this on the very first homework assignment. So if that was you, good on you for doing that. We were looking in velocities. And so when you calculate a derivative, you said meters per second, or it might have been feet per second, if I can't recall the quite unit. Same idea here. We really should put in the unit on this one because that's going to assist us with this part. Interpreting what it was we actually calculated in the first place. If you can put a unit to that, that's half the battle in interpretation sometimes. But here's where Leibniz notation really, really shines. We hinted at this a little bit. If we're in a particular application, if there's a real context behind the problem, Leibniz notation is sometimes preferable for several reasons, and this is one of them. It tells you the unit immediately. You look to the numerator, dl. You look at what L was. L is measured in inches. So that tells us our result, 1.718, has unit of inches in the numerator. You could say per, but I'll go with the fraction bar instead. Then you go into the denominator, it's dA. So the variable is A. Same idea, look up what A was. It's years. And so the derivative is always a rate. It's an instantaneous rate of change when A is 12. And because it's a rate, our units are being divided in inches per year. So that's kind of a nice way to put together units in a nice cohesive way that mirrors Leibniz notation in the very first place. So that's the second step. We now know what the derivative is in terms of units. Now we're putting it all together using the number, the unit, the fact that we have an overall context of it's about those fish. So we need to return to that context and say what we just computed. Any questions or comments at the moment? Okay, like we hinted at before, this is the major thing about calculus. The thing we want to keep separate in our mind is for that cubic polynomial, that's the length. And if we plugged in 12, we would know the predicted length of the fish when it's 12 years old. That is not the length of the fish when it's 12 years old at all. So we have to separate that from our minds. We'll say this instead. When the fish is 12 years old, we must say that part right here because the derivative is going to change if we said evaluate it when A is 2 or when A is 8, for example. It's growing at different rates depending on where it is in its life cycle. So that part is required for this interpretation. So when the fish, and we can say, we know we're talking about the Alaskan rockfish, so I abbreviated it there. When the fish is 12 years old, from that number, we can say it is growing at a rate of 1.718 inches per year. Not sure what to highlight. Maybe I should keep the highlighting more like this. Just to make it more compatible with step 2. But that would be the complete interpretation. Now, the word growing is also pretty important here. The only reason we said that the fish is growing is because the derivative is positive. Probably wouldn't make sense for the derivative to be negative, unless there's certain fish that shrink after they get certain age. I'm not a marine biologist, so I couldn't really answer that definitively. But for this kind of situation, I imagine the fish is just always growing until its growth rate slows to a near stop. And so we're always kind of expecting positive. But if we had a different context, if that number could have been negative, we'd have said shrinking instead, or decaying, or falling down, like with velocities and so on. So the sign of the number tells us when things are going up or growing, or things are going down or shrinking and so on. So this is what the practical interpretation would look like. We still don't know how big to expect the fish until we plug 12 into the original quantity. But what we do know is at age 12, this is like the speedometer of how fast it grows, 1.718 inches per year. And so that's the wrap up of the applied problem on this one. We looked at a lot of different kind of derivatives. It gets pretty abstract as you go through these notes. So we'll do applications like these even before our big application chapter 4, just to kind of ground what we're doing with all this material into something more close to real life, where this is just pure abstract math on its own. The value of it is this kind of work and this kind of interpretation. Well, any last questions or thoughts at all, folks, before we close out this section? Okay, well, as usual, we have just a little over 10 minutes of time left, about 12 minutes together. So I want to just show about what the next section is going to go into before delving too far, too fast. Let's kind of orient ourselves to what's coming up next. We mentioned that there were certain functions we just could not differentiate in the last section. Reason being is functions were being either multiplied or they were being divided. The section 3.2 is now going to tell us how to handle a function when you have two multiplying together. This is beyond the constant multiple rule. We're assuming both functions vary with x. So for differentiating a product of functions, not like 3x, more like x times e to the x. This is the process we have to take for the product rule. If we happen to be dividing functions, this is the process that we have to take with the quotient rule. Let me blow that one up as well. So we're going to study these really very, very carefully just to see what the process looks like when we come back on the lecture next time. But just for the sake of just a quick look at these, let's break down the process to see what it's saying. The process says you have two functions, an f of x times a g of x. So a typical example down below might be something like y equals x times e to the x. We have not done any function close to that one in the last section notes whatsoever. We purposely stayed away from it because now that's not a constant, that's a bona fide function of x. And so is that one. X and e to the x are like the f of x and like the g of x. The derivative of this function is not the derivative of x times the derivative of e to the x. And same from when we saw product of functions in the last section. In the last section, when that came up, we had to expand out our functions. The process instead goes like this. We differentiate one function, multiply by the second, add the first function, multiply by the derivative of the second. So it's an interesting little game called now the product rule altogether, which will give us the right result. So if we want the derivative on this one, here's the thought. This is our big formula, but really, if there's two functions you're differentiating, there's four placeholders is what this formula is telling us. So we can break it down in this kind of format. Put in a placeholder with a derivative on it. Placeholder will just copy a function. Another function getting copied on that placeholder. And another placeholder with a derivative. My color coding is going to emphasize where the derivative actually occurs. And then we just copy the functions in this particular order. So if it goes x e to the x, we can put x here, e to the x here, and then just copy that pattern once again over here, x, e to the x. So that's all the product rule is trying to say. This is the right way to arrange a derivative when you're doing a product of functions. A pretty bizarre rule altogether when you're taking a look at that. If you're curious on how this works the way it works, I put a really fast write-up for the proof of the product rule. But all it does is it uses the definition of the derivative, uses a little bit of trickery inside there. And this is what you get using the definition of the derivative like 3 different times. Our result is that. Then our work is just about done. The derivative of x is 1, so this becomes 1 times e to the x plus x. Notice in these spots where you see the g of x and the f of x, we're just copying them down. These parts where they're highlighted, where the prime symbols go in the formula above, that's where you're differentiating. So here you would get e to the x. And it does simplify a little bit further because of that times 1. So the end result is that y prime is e to the x plus x, e to the x. And so that's the whole punchline to that function through the product rule on that. Well, we did, folks. That's what the product rule looks like. But any questions or comments so far getting through that one? Okay, here's where it gets, again, a little bit tricky because we have a lot of rules altogether with 3.1 and now cracking open section 3.2. For this particular function, the product rule is required. If you say something is required in mathematics, that's a very, very strong statement. And let's throw down a new function. Y equals 8 times e to the x. Now for this one, you know what? You can use the product rule. It really works out, but you're working hard. You're making a mountain out of an anthill when you do that. So the comment on this one is, because that's a constant, the product rule should not be used. Not because you'll get the wrong answer. You should practice this on your own time just to see how it goes. If you use the product rule, you'd be putting 8 here, but when you differentiate that, it's a 0. So it kills off the e to the x function, and you get the right answer when you go over here to that part. But what you should be using instead is use the constant rule. Excuse me, use the constant multiple rule. So you would get y equals 8 is the constant multiplying. Now differentiate e to the x, and you're done. Nothing further about this. So the major thing to keep an eye on when you're thinking about the product rule is, do you really have two functions that vary with x, not one of them being constant, and they're being multiplied, and there's nothing you can do to simplify to eliminate the fact that there's two functions multiplied. For example, in section 3.1, there were some product rule problems that came up, like say, that one, that's a product rule because it's one function times another function. They happen to be the same. But if you use algebra, you can sneak out of the product rule. That's highly encouraged, and then just differentiate in the normal way. There is no algebra in the world that allows you to simplify that and avoid the product rule. Not writing down finitely many terms, because e to the x cannot be simplified in that kind of way whatsoever. So we had to use a product rule, no way around it. But once you identify a constant, you'll notice when things can be simplified really fast, use a more available rule. We'll make similar kind of concepts with the quotient rule, so for the purpose of saving a whole lot of time. So when we come back on Thursday's class, we'll practice a couple product rule problems, look into the quotient rule, practice those, see how they go, and then go from there. But any last questions or thoughts at all, folks, before we call tonight? Okay, well, this will be a good stopping point for us. I'm going to try not to start a brand new set of examples or an example that might take us beyond the 7:10 time, because I know your time is important as well. So we'll always try to say around 7:05, wrap things up, make a final call for questions. And if we end a couple minutes early, that's not the worst thing in the world. But have a great night, folks. Thanks for all the questions and comments and spotting any of those weird errors like transposing the numbers on that earlier problem today. We'll return here when we come back on Thursday. Have a great night. Thanks. Have a good one.